Is my screen visible?
Yes, sir.
So, welcome to today's session. Uh, I hope everyone here was part of the last session, the introductory session that we had. So technically today we are meeting for the second time, but this is the first actual session because last one was an introductory to what the field is and what the course is about. So today's session will be the actual beginning of the course. Today's session also will be a bit theoretical. We'll delve a bit deeper into VR and AR and understand what tech stack in Unity exactly we'll be using and what exactly is used to develop these things. Apart from the general Unity framework, what other tools are available for us to explore and use. So, and also, if time permits, we'll install, look into installing Unity and how it is managed, what different components of that are. But primarily, we focus on understanding the different concepts, some more theoretical concepts that go into the development of VR and AR. Um, so let's start. Some basic things before we start. One is basically you will have an attendance to mark after the session. Once the session is over, you will be shared a form with on the I think on the Teams itself, and you have to fill it within 15 minutes. It will be an attendance uh, form as well as an evaluation. There are 3-4 questions from today's session, which are general MCQ type questions. So if you pay attention in today's session, you will be able to answer them. And these questions will also be part of your evaluation towards the certificate that you'll get towards the end. Uh, the certificate that you'll get would indicate some grade, and this daily kind of evaluation will be part of uh, that grade.
So just sorry to interrupt, sir. So the form would be put up in the chat, and there is a request for everybody to keep a screenshot of their own. You have to take a picture of yourself before, as it would be needed in the form, with your name and face visible. And as sir said, it would be open only for 15 minutes. It shall be closed. So you have to be on time with it. Sorry to take your time, sir.
Yeah, no issues. Is there anything else that should be mentioned?
No, sir, that's about it. And that this form would be done every time we'll have a class. So do remember to fill it as sir said, you would be marked on the basis of that form. Thank you, sir.
Yeah, cool. Okay, so let's start. So course objectives, we discussed this briefly in the last session. We'll cover main 4 topics: Unity basics, C# scripting, game development basics, and VR and AR development, along with some bonus topics that I discussed, which was basically using Unity for artificial intelligence and Instagram filters through a different tool, which is Spark AI. So let me show you detail of this outline, how we are going to go about covering this whole thing in 30 sessions. I can share with this list with you later as well. So basically, the whole course is divided into 30 sessions, where and each session will be a part to one of these 4 topics that is there, either introducing Unity or basics of C# or game development basics or VRAR development. So, and the course is structured in this fashion where we start with an introduction to some basics of this XR, VRAR. Some of this we have already covered. Some things we covered today. Then introduction to Unity, what is the different views, what are the interface, how Unity is generally used, things like that. Then setting up the project, scripting. So then scripting will come, then user input, and each like the whole session, there are also parts like when we complete one specific session in Unity, like in session, some set of sessions, like 5, 6 after each 7, 6, 7 sessions, there's one uh, project, small project that will be implemented. So this is something that will help you build your portfolio. Like we said in the introductory session, there will be three basic games, one VR and one AR game. Apart from this, also it depends on you how much time you give and how many things that you can make. So like after 6 sessions, there's one game that will build something, mini project, which will do some specific functions, and you'll understand what you have learned till now. You'll implement that in an actual game. Then we'll move on to game development with gameplay mechanics, physics, and other things. And then again, one game. Then animation, effects, a bit of AI, how we implement AI inside games in non-playing characters, some user interface, how we build and deploy these things. Then again, one more game. And then we will come to VR, and VR will have introduction where setting up the SDK and using input in the VR, then VR interfaces and all those things. And a lot of these concepts that you learn initially in the game development part are as is implementable in the VR part as well as the AR part. So some of it is just changing how you think about it and implementing it with a different perspective. Then again, by the end of VR, we'll have a project in VR, and then we start with AR. AR we'll have uh, 2, 3 different things to do, smaller things, and then one AR project. Then 3 bonus sessions are there, which basically is 2 of them have to do with AI, how Unity can help with AI, and one is face, like AR filters with Spark AR, which is uh, Facebook and Instagram filters, basically. So this is an outline of the course and the objectives of the course. So for today's session, uh, the objectives are to look into VR more deeply, understand some of the components like optics, display, tracking, and user interface. Looking into AR more deeply and understand marker versus markerless AR and SLAM technology. And then we look at the Unity tech stack, how exactly, what different tools we'll be using, and then we'll look into installing Unity. And if time permits, we'll start with the actual hands-on sessions that we are supposed to have from the next session. So this is like we covered. This is just to start from where we left last time. Virtual reality is basically a three-dimensional computer-generated environment. Can be explored and interacted by with a person, uh, and it has like the user has the ability to manipulate objects or perform a series of actions. So we know what virtual reality is, but now let's look at some of the components of virtual reality, like optics, display, tracking, and user interface. These are more major components uh, that are involved in the development and the usage in actual real life in virtual reality. So, uh, when we are talking about virtual reality here, all of these things that we are talking about is mostly head-mounted display based VR, where you are actually wearing some kind of a headset and experiencing a completely different environment. So this is what we mean by virtual reality here. So basically, when you are wearing some headset, how that headset is actually helping you see a different environment. What is the hardware, like how is the hardware actually made so that you're able to see and perceive what you are actually trying the user to perceive. So in natural life, like right now, if you look at objects that are at infinity, so like objects that are very far, the eyes, your eyes acts as lens. So you have the ciliary muscles that are basically kind of lenses that are natural lenses. So when the object you're looking at a object which is very far from you, assuming that the distance, let's say that the distance is infinity, where like you are looking at the sky, then the lenses, the natural lenses of your eyes are in a relaxed state. But as the object moves nearer towards you and comes towards you, the actual lenses, the shape starts to bend. And this basically, why it is done is basically whatever we perceive, whatever humans perceive, is basically some light falling on the object, which we are able to perceive through our eyes, through these lenses. And what happens is basically the lens that are available, the lens that is available to the human eye is basically uh, contracting the light inside your eye at the back of the eye towards uh, the retina. So this is basically where you're trying to contract the light that is captured from the environment. So since the whenever the object is at a very far distance, you don't capture a lot of light. So you are able to see at infinity also you are able to see blurry small objects, things like that. So you are not paying detailed attention. But when you are at a specific distance, like let's say 400 meters, 200 meters, even 800 meters, then you are able to see, to some extent, you are able to see and differentiate between the objects. As it comes closer towards you, you are basically trying to manipulate the lens in your eyes, and this is all being done naturally. You don't actually have to physically implement anything. You don't have to think about doing anything. This is all being naturally done. As the things start moving closer to you, your eyes will change, the lenses will change its shape, and again try to maintain the light that it is capturing. It will to maintain the light captured to fall at the back of the eye, which is at the retina, to form the exact picture that is actually there. So if I move my finger very close to my eye, this finger is now blurred. So how are we able to actually see something when we are wearing the VR headset, when the lenses are actually towards our eye? So from this near eye display, what we want is something to actually go on the retina. So this is why some special lenses are created in VR headsets. Not like normal lenses do not work. Like we generally, for people who have some uh, disorder in their eye, which is they can't see very far or they can't see close, they wear lenses of different kinds, right? To help them, to aid them in forming the images again at the back of the eye. So when we say that some person has some form of power, like eye lens power in their glasses, we are basically saying that this is a support that they need to actually form that image at the back of the head. So VR lenses are similar in the sense that what we want to do is capture something that is being displayed very close to the eye and magnify that in the sense in and display that at the back of the head. So the size, shape, and the placement of lenses impact the VR experience very highly. If you have used any VR headset, any immersive head-mounted display, you will see that they have an option to set the distance of the whole headset from the eye. You can basically change the width, like the height or the width, whatever you want to call it, of the actual headset that is there. You can change the interpupillary distance, and you can shift the lenses up and down also. So basically try to adjust the lenses inside the VR headset according to your personal preference. So some of the things that this impacts, like it actually impacts, are the field of view, focal length, and optical distortion. So field of view is basically the actual view that you are able to see. So in general, like right now, you are able to see more than 120 degrees in real life with your natural eyes. In VR, that is limited to 60 degrees or 30 degrees, depending upon what kind of lenses that are generally used. And this basically creates, this is basically dependent on the focal lengths of the lenses that are used, and also might cause optical distortion. So if you don't have the actual correct settings according to your personal preference, you will not be able to see everything very properly. Some things might be blurred in the VR environment. Some things might not seem proper, like the actual distance to them, you will not be able to perceive. So these are optical distortions that occur if you are not actually able to implement VR lenses properly. Then so comfort and cost is there's a trade-off between comfort and cost while developing VR lenses. This is the video explaining what I just said in a smaller and it's a good video. So let's have a look at it.
Eyes focus on something far away. They focus on infinity.
I don't think you are able to hear the audio.
The lenses of your eyes are in.
No, sir.
Yeah, so I think I didn't share with audio. Just a second. My screen is visible, right?
Yes, sir.
If your eyes focus on something far away,
Are you able to hear the audio now?
Yes, sir.
Okay.
if your eyes focus on something far away, they focus on infinity. That means the rays of light are parallel and the lenses of your eyes are relaxed. If an object like this little fly moves closer to your eyes and you want to keep it in focus, your lens bends and breaks the light differently. To keep the fly in focus, all the light from a single point on the insect needs to be focused on a single point in the back of your eyes. If the fly comes too close, the lens cannot bend enough and you lose focus. This is why VR headsets need special lenses. So the angle of the light from the lenses is corrected so that it can be used by your eyes again. Because the light rays hit your lens at a different angle, you perceive the image as farther away than it really is. To make the headset lenses thinner and lighter, some VR headsets use Fresnel lenses, which are lenses with the same curvature as regular lenses, but they're segmented. But using Fresnel lenses means that you have to make compromises. You can create lenses with many segments, which results in a sharper image. However, you lose light that gets scattered at the peaks that do not have the right curvature. As an alternative, you can create Fresnel lenses that have fewer segments, which results in less scattered light and more contrast, but will also give you images that aren't as sharp.
So yeah, so basically this was about how different companies are creating different lenses. So this is why when you uh, look at different hardwares, the cost of the hardware are drastically different. Some cost as low as 30,000, 40,000 right now, and some are in the high segment, 2 lakhs, 3 lakhs as well. Even consumer grade VR devices are this costly because one of the major drawbacks or one of the major things that they spend money on are these lenses, which are called as Fresnel lenses, where they are not creating a single segment of the lens, they are segmenting the lens into different forms, and basically a lot of research is going on in improving this. Now, uh, I like in the recent years they have stuck a wall on the hardware side, so they have started improvising on the software side by using machine learning or AI-based rendering of the system, so that some parts where the lenses are not able to actually give you what you want, AI is able to capture that and render those things. So it's very new area. It's not actually available to us. A lot of things are not available to us directly right now, but it's up and coming, and we'll be able to see some of these things in the near future in the development side as well. So next is basically, so after you've placed a lens in front of your eyes, behind that is a display that is rendering something. So now there are two type of displays that can be there, uh, like how it is being rendered. Basically one, uh, not two kinds of displays, basically two kinds of systems that render on this display. One is basically where the compute is available in this headset itself, and it is rendering on this display that you have. And the second is basically compute is not available on this headset. It's either on a mobile phone or either on a computer system, depending upon the cost of the device that you're using. And then that is being rendered onto the display that you have. So when you're using a mobile phone, you're basically mobile-based VR. If you look, there's a section in front of the VR headset which opens up, and you place your mobile inside that. So your mobile phone is the actual display that is being used to render when you are using mobile-based VR. In case of systems that are completely standalone, then you have displays right there and the compute system as well right there. So compute systems are computing and then rendering to the displays. In case of systems where PCs are used, PC-based VR, there your compute is being done on the PC and then rendering it on the display that is there in the VR headset. So all these different kinds of systems basically create different kinds of rendering latency. But in general, also there's a motion to photon latency, which basically means that when you move your head inside VR, what is the latency between the movement that you have actually done and the actual rendering of the scene that you are moving towards. So in general, to implement a uh, non-breakable scene, so you don't see breaks inside the scene that you're implementing, this motion to photon latency needs to be under 300 milliseconds. There are other added latencies. If you're using PCVR, there might be issues with your Wi-Fi system, and there can be latency because of that. If you're using mobile-based displays, your mobile can be slow, and some of the things can be some latency can be there because of that. So there are different latencies which are possible based on the rendering system, but uh, generally the intent is to keep this latency at as minimum as possible. And then there's basically some kind of motion blur. So like if you don't implement some of the other things, like a lot of things when you actually use frameworks like Unity or Unreal or any other system that is actually giving you SDK for VR development, they implement a lot of these things already. They have created this whole rendering pipeline already for you. So you don't have to implement anything in a real sense. You don't have to implement these things, but it is better to know what is happening. So in general, what you want is to reduce this motion blur. Like when you are looking around in the environment, how late is something that is actually where you are seeing actually gets rendered. So generally in systems that when we use Unity or Unreal or any other framework for development, you will not generally see this issue, rendering latency issue, because this has been resolved a lot. So what happens is basically it is being displayed frame by frame. So generally, whenever you are using any kind of a system, playing any video game or playing any video itself, watching a movie, there's a concept of frames per second. So higher the frames per second, higher the resolution, basically higher the quality that you can see of between the animations. So between the different screens. So if you see a cartoon or an animated movie which has been rendered at, let's say, 60 frames per second, then you won't see the latency between the movement in a character's animation. But if you render the same thing with in 10 frames per second, you will be able to see that the movement of the character or the animation is not very crisp. So this is why in VR, frames per second is important, as well as because there's movement, continuous movement of the actual where what to render. There's also this concept where to remove this motion blur. What is done is basically after each frame, like each frame, let's say each frame is rendered for t time, then the end block delta t time is reserved for a black screen. You won't actually see it because it is being rendered at a very high frame rate, because it is being rendered at 30, 60 frames per second. And each frame has a very small window where it's a black screen. So this basically helps in creating a low persistence and system and eliminates motion blur. And it helps in creating an illusion of the movement being crisp. So by not rendering some of the time in the frame, you are able to remove this motion blur and create an illusion of crisp motion. So you don't actually have to implement this. This is already implemented, and a lot of different techniques as well now have come up, which are AI based to uh, reduce this kind of motion blur and other latencies in the display. So next concept is tracking, which is basically trying to understand where you are in space. So one of the major uh, components of VR would be to track your movement, so that with respect to the headset, with respect to the controllers that you're holding, so that it is able to implement whatever you are trying to implement, as well as it should. So for this, basically IMUs, which are inertial measurement units, it's basically a small hardware which measures, in a sense, does the work of accelerometers and I forgot the other word. Your phones have inertial measurement units, which basically measure the how fast the movement of a phone is and in which angle the phone is rotated. And every VR device also comes with these, so that you are able to understand the movement of it. And there are two kinds of tracking. One is inside out tracking, and one is outside in tracking. So inside out tracking is basically where you do not have any external sensors in the environment. You are basically perceiving everything just based on your VR headset and additional trackers that are there in the uh, controllers. So this generally there are this basically leads to varying forms of degrees of freedom. So a 0 degree of freedom would mean that your VR screen is stuck exactly with your headset. So wherever you move, even if you move right, your screen will move with you. So you don't have any freedom to actually implement any movement. You can control things through your controller, but visually, like actual physical movements, whatever you do, will not correspond to anything. So like this would be like playing a video game on a desktop or on a mobile phone, where basically where you move your head does not actually change what is happening in the environment. Like the environment is stuck there, it does not move with you. And then 3 degrees of freedom basically mean that I have a video next in the next slide, which basically shows this a bit better. And then there's 3 degrees of freedom basically allows you three kinds of rotation. One is like head movement and movement inside uh, your head movement basically, and not your physical movement. So whenever you move physically in the environment, 3 degrees of freedom won't be able to capture that, and it is only able to capture your head movement and able to render the scene with accuracy even then. And then 6 degrees of freedom are basically where you can move inside the virtual environment physically, as well as rotate your head, move your completely turn around, do anything that you want, and the environment stays there. So higher the degrees of freedom, higher is the immersivity in the environment. So this is a video of demonstrating what basically all this degrees of freedom would actually mean. So if you see in 0 degrees of freedom, assume this is your actual environment that you're interacting with, the box that is in front of you. So in 0 degrees of freedom, it is wherever you're moving, apart from this movement, if you're doing any rotation, any movement, it is moving, the screen is moving with you. In 3 degrees of freedom, only the physical movement, the screen is moving with you. When you're rotating your head, the screen is not moving, right? And in 6 degrees of freedom, the screen is not moving at all. The screen, in the sense, the environment is not moving at all. You can move wherever you want, interact with it, however you want. So these are 3 degrees of freedom. It is said that higher the degrees of freedom, higher would be the immersivity of an environment, because you are able to interact with it like an actual environment, like you are able to interact with things in a real life. So that's about tracking. Then comes user interfaces. So there in heads-up display, the major challenge is that the display is actually too close to your eyes, right? It's in front of you, and you are able to generally in any scenario, you will be able to perceive the world that you have created as a first person view. So what happens is, if you put some scores or something in front of the user, this generally breaks immersion. So there are other methods of implementing uh, this user interfaces in VR, either by using world space UIs or strategically based UIs. I'll talk about this in just a second. The problem with heads-up displays, like uh, talking about the entertainment sector generally, like games, is that you want the user to be aware of 3 or 4 different things. Like, let's say if it's a shooter-based game where the person has to go in an environment and shoot some enemies, so you want when you play it on a general desktop-based scenario or a mobile-based scenario, you will be able to see the number of bullets that you have left, a small mini map of the environment marking you and the enemies around you, uh, general health of the player, some other features that can be there, your teammates can be mentioned, things like that. So this is generally what comprises of the heads-up display, with basically showing some information to the user. So imagine like same information that is being displayed on a screen comes just closer to your eye, and you're in VR and you're able to see this information. And uh, because this basically you are experiencing this in a first person sense, you'll have to manage how to occlude it, how to implement occlusions with different things in the environment and such things. So basically, to avoid doing this, to avoid breaking the immersivity of the user, uh, there are 2 ways that you can do it. One is world space UIs, basically means that implement interfaces or whatever you want the user to see somewhere naturally in the world. So implement, like, let's say you want to show the health of the enemies that the player is killing, then you can show it on the top of the head of the enemy instead of showing it on a GUI in the user's heads-up display. If you want to show the number of bullets that the user has left, you can show it on top of the gun itself. So these are world-space UIs, and a combination of strategically placing where you place the components. So this is kind of like trying to understand best practices for designing user interfaces in VR, and as well as AR also has a lot of these. So a lot of new companies that implement games or different things in VR now have come up with their own design principles for VR and have their own user experience and user interface principles specifically for VR, and I can share some of those with you. So, but this is the general problem that occurs, and the solution is placing the interfaces strategically in the environment using world space rather than user space interfaces. Then one of the major challenge in VR is motion or simulator sickness. which is generally caused due to the mismatch between the body's sense of motion and the visual system. So why generally motion sickness is caused? Like we talked about motion blur, uh, that is one of the major reasons why this is caused. So basically, you are perceiving that you are looking in X direction, but your visual system is looking in Y direction. There's a delay with your where your physical body is and where your virtual rendering is being done. So due to this causes a lot of motion sickness, and motion sickness is very harmful as well. Like some people vomit a lot and feel nauseous. Some people feel vertigo, where basically they feel a sense of falling down and things like that. So when we do any kind of research in VR, generally any simulation or any game or environment that we make, there's generally a simulator sickness questionnaire that is involved, which is a list of questions that is asking the user if they feel any discomfort while playing the simulation. So the general idea to create any VR simulation or any game is basically that it should be able to uh, like the user should be able to use it for a prolonged period of time and not just for a limited period of time. So uh, like the usage time should not uh, challenge the user to use VR to implement motion sickness, to not implement, to basically have motion sickness. So that is why a lot of research is being done in this area to, and generally also like if you are launching something in VR or complete it, and this is not a challenge with AR generally, this is a challenge with a complete immersive VR scenario. So if you launch something, you do user experience tests and you take simulator sickness questionnaires and try to understand where something might be flawed. So this is about motion sickness. Then let's move on to augmented reality. Like we talked about this, any superimposed augmented reality basically superimposes a computer generated image on the user's view of the real world. So we'll talk about some of the things in augmented reality, the devices, marker versus markerless, SLAM, and geolocation. So devices, I think this we touched about in brief in the introductory session as well. There are head-mounted displays, photographic displays, and handheld AR-based devices. So head-mounted display, there are two things. One is optical see-through and one is video see-through. So optical see-through is displays where basically you are, even if you have a head-mounted display, you are able to see the actual real environment with your direct eyes and not through something else. Computer-generated images are there on top of this. Then video see-through displays are basically where your camera is perceiving the environment and then you are able to get that display on in your headset, and not you're not able to see the actual environment directly. You're seeing that also as a rendering of what the camera is seeing. So right now, if you see devices like Oculus Quest, they are implementing a lot of things in pass-through. They are calling it pass-through, which is basically video see-through, where they have cameras in their devices, and you are able to see the environment around you through those cameras, whatever the camera is capturing, and then they're implementing a lot of features there as well. So it's a VR device which is also trying to implement AR things. So then there are holographic displays, which again we talked about in the last session, where there are right now things that like implemented through fast moving fans. There are smaller animations that can be implemented. Actual real holographic displays are not possible as of yet, which we see in movies and different sci-fi scenes. Then there's handheld AR, which is basically your typical mobile phone based AR, where you are able to hold the device in your hand and try to render whatever computer generated image on top of your real scene. So you are able to see it is technically it is of video see-through because you are perceiving the environment on which the rendering is being done through the cameras of your phone, and then augmenting some things on it and then seeing it on the screen. So technically it is also video see-through. So this is about types of devices. Then there are two major forms of AR. One is marker based, one is markerless. So marker based generally means that the whatever you are generating in an environment is generally tethered to some marker, and marker can be an image, a specific image, or a 3D object. So there are two forms of marker that are there, markers that are there and are implementable. You can create a 3D object, an actual real life object, use a real life object as a marker. So like, let's say you want to, you are creating a training system for a military tank, and you have the components of the tank laid out on a table. So you can use each of those components as a marker. So whenever a user puts their device on top of that marker, it will show some display. So it will show some information about the specific part. So that basically is a 3D marker. And other form of marker is basically something to understand it easily. You can think of it as a QR code. Although it's not a QR code exactly, it's just basically that we are using some abstract images and mapping some feature points in that image to a specific object that we want to display on top of that. That's it. Then markerless are basically AR where we're not generally fixing where or fixing how to actually render something in the real world, but there are two or three different ways that this can be done. One is basically doing airdrops, so dropping objects anywhere in the environment at the air and anchoring it to some location in the air itself, with the perception of wherever you start, that becomes your 0, 0 location. And in the environment, you drop things in the environment and are able to perceive it later as well. Second is trying to augment things on a horizontal or vertical plane. So this is something called plane tracking, which we learn when we implement AR. Either a horizontal plane or a vertical plane can be recognized using any camera or like any AR SDK, and then on this either horizontal or vertical plane, you place some object that you want to place. So this a very good use case of this is basically trying to implement things like furniture testing. So in your house, you can generally try to test furniture. So a lot of new companies have implemented this where you can test before buying in your house itself. And one major again example of this is Pokemon Go, which was very famous 3-4 years back, which is markerless AR. Then talking about SLAM, which is one of the highly used technologies in markerless AR. SLAM is basically simultaneous localization and mapping. So what this means is basically it's a very old algorithm which basically started with when we were trying to understand the environment around us with the perspective of it's used in various different applications like sonar technologies in submarines or aerial technologies. Initially, now then it moved on to self-driving cars, AI-based rovers, things like that. And now it's also highly used in AR, where basically you are localizing yourself and then mapping the environment around you. So like in the video that you see, the car is the local, like car is doing the implementing the algorithm and it's localizing itself and then mapping the environment around it. So in a general sense, we are able to implement object and scene recognition from it. So we are able to recognize different objects that are there in the environment, as well as trying to understand what scene we are in. And then using SLAM only, we are able to recognize plane, like I just said, there's plane tracking that can be done either horizontal or vertical. So using SLAM, you are able to track those surfaces as well. And then there's feature detection where using SLAM, you're able to detect specific features. Like if you see, we are able to see that it is a pole with points, rendering points that are there. We are able to see that it's some kind of a pole. Humans are being rendered. So you are able to detect what, some based on some features, you're able to detect as well what actually is in the environment. So this is about SLAM, and then using geotagged features in augmentation. Like this is again a major feature where you are linking the augmented feature or augmented object with a geo location, not with your location, but a general GPS location in a sense. So, like I talked about Pokemon Go was a combination of markerless and geotagged augmentation, where basically uh, when you go to some place, you'll find some Pokemons to catch in that specific environment. Then you go to some other place, there will be a gym or training area where you can train and find things. So, like basically, different environments in the real, different places in the real world have different meaning in the augmented world. So, the augmented objects have been geotagged to different places in the real world. So, this is what geotagged augmentation generally means. So that was about a brief about Unity and, sorry, not Unity, VR and AR. Then moving on to what we'll actually use in Unity. So we general base is Unity, where we learn all the basics of game development using Unity, which covers a lot of different topics. And then for specifically for VR AR, there are few new tools that Unity have made, some different packages that we'll be using. So one is basically looking at the Unity XR tech stack, where generally what is done is basically like a few years back, what was done is every company that was making their own VR headset or AR device, they used to provide us with their own SDKs to implement everything. So there was no general to and fro between different frameworks. So if you have to implement something for an Android phone, you will be able to implement it for Android only. Talking about AR, uh, if you want to implement something for iPhone, then you'll be able to implement only for iPhone. If I implement something for HTC Vive, then I won't be implemented for Oculus Rift. This was basically 4 or 5 years back. So then Unity came up with a framework where basically all these different SDKs are managed by Unity's XR subsystem using the Unity XR plugin framework, where basically all these individual components or individual third-party plugins or any provider plugins or SDKs are basically interacting with the Unity SDK, and we are implementing the Unity SDK generally. We can implement the device-specific things also if we want for specific things. Like some things might not be available, everything might not be available in the Unity XR SDK. So sometimes we use some of the things that are device specific as well. But in general, Unity, the idea of creating a Unity XR SDK on top of these different individual SDKs, so that you can, when you implement something in Unity, you are able to transfer it to different systems without changing a lot of code, which is basically one of the beliefs or the mission of Unity anyway since the start, which when they were doing builds of different subsystems through the same code base itself, which was cross-platform builds. You can do Windows, Unity, Linux, Mac, anything you can build directly from the same code base. So then on top of this Unity XR SDK, there are two tools, major tools that are available. One is AR Foundation, which is specifically for AR stuff, and then there is XR Interaction Toolkit, which is for both the things. There are some things that AR is also able to implement. We are able to implement for AR as well in the XR Interaction Toolkit, but majorly it is for VR development. And then finally, we have the AR and VR apps. So there's also something called Mixed and Augmented Reality Studio from Unity, which we'll not be using, but it is basically a set of tools that has been created on top of the AR Foundation tool to basically test different AR and mixed reality systems. It's a paid feature available by Unity, which we can look into if required. But generally, it's just a testing framework in a sense. But they have implemented some new features, so if required, we can look into that as well. So this is about the how Unity is implementing the XR tech stack. Specifically talking about AR Foundation. So AR Foundation, this is a bit old image where if you see here, supported and pending is there. So some of the things that are not marked here, I think might have been completed by now. This is specific to AR development. Some of the functionalities that we want are pass-through video, device tracking, radar, plane tracking, face tracking. These are things that we talked about. And then device-specific features that are there. ARKit is for iPhone. AR Core is for Google's Android. Magic Leap is a separate device. HoloLens is a separate device. HoloLens is from Microsoft. So these are four devices. Generally, we'll be using, because Magic Leap and HoloLens are enterprise devices which are very costly. We'll generally be making it for mobile-based devices. So either iPhone or Android. So if you see here that iPhone provides a lot more features than Android. This is because in general ARKit supports a lot more features than AR Core. Okay, so that was about everything that we had. Then let's move to Unity. This is where I wanted to move to Unity, but we are out of time. So, but we'll talk about some of the things of how to download and install, and then we'll end the session. So the first thing that you should do is basically get the GitHub Student Developer Pack, which is basically a pack that allows you to get some softwares pro versions for free while you are a student or a teacher or anything like while you are related with academia. This is something that allows you to a lot of different tools for free. So look into this, sign up for this. This will allow you to basically get Unity Pro version for 1 year for free, and then you can subsequently enhance the update every year while you are a student as well. So there's no much difference between the Unity Pro and Unity Personal, like free plan. There are different versions of Unity that are available. Versions in the sense different plans of Unity, but Pro is not a requirement. You can also use free version. But because you are students and you have the capability of getting this for free, you should get this, so that some of the features that are there in the Pro version, you should be aware of that as well, which is basically customizing the splash screen, which is when you open an app, Unity logo would not come. You can customize that to your requirements, and you can access dark mode and while in the Unity header. These are some of the features that you can implement. So first is sign up for this, then go to search Google for Unity student plan, and you will come to this page where you will apply for post-secondary students. Once you click on get started, it will ask you to log into your GitHub account and then make the verification from there. So I am already logged into my GitHub, so it is asking if I would like to apply the Unity student plan for this VMIT account, which is my GitHub ID. So this will walk you through the process of getting the license for your Unity ID, connecting your Unity ID with your GitHub ID. And if you have a GitHub GitHub student account, then this will basically give you the Pro version right away. Then coming to actually downloading and using Unity. So there are just search Unity download. You will come across this page where basically there are two ways you can download Unity. One is to choose specific version of Unity. Unity development is very exponential is carried out at a very exponential rate. Every few days, there's a new version of Unity, and you would not be generally able to keep up with that. So generally, what you would want is to download a stable version of Unity, and whatever you are learning or doing is basically doing implement on that. So generally, you would try to use a long-term support, latest whatever is while you download Unity, just go for latest version that is there in the long-term support release. So this is one way to do it, where you choose your Unity version and download it. And the second way is to download Unity Hub. So Unity Hub is a small software, which basically allows you to manage the whole of Unity subsystem. So let me show you Unity Hub. Once you download and install Unity Hub and log in to the Unity Hub environment with your ID, this is something that you'll see. So you go in and you'll sign in here. And once you sign in, then you will be able to basically see your licenses, manage your license, whatever you have. So like now I signed in, and then I can go to account settings. Sorry, not this. Manage licenses, basically, which is basically this is where you will be able to add the professional license or the pro license if you are able to get it through the Unity student account. So once you do this, then you go to installs and install editor. So install editor mein official releases, long-term support, whatever is the latest. Latest right now is 2021.3.4 F1 LTS. So this is the version that you should generally install. So yeah, that's all from my side for today. Do we have any questions? So yeah, that is the end of today's session. Yeah.
Sorry, sir. Sorry to disturb you. Please continue. It was just the end of the session, kind of like an announcement.
Yeah. So like, yeah, that's all from my side. If there are any questions, you can put it in the chat box or raise your hands or whatever you want to do, however you want to implement that. That's all from my side for today.
So I had a question, sir. When I'm currently on Unity ID, so the only option it currently gives me is that if you don't have a Unity ID, please create one. And there is no other thing for GitHub per se.
Which is, look, if you go through the student plan. Okay, so create one. Like, do you have a Unity login? Like, have you created a Unity account?
I did, sir. Yes, sir.
Okay, so once you log in to that, then you will be able to connect through that, I think.
Oh, thank you, sir.
Yeah. Once you log in, then you'll be able to see.
Okay, sir. So for everyone, please turn on your cameras for your screenshots. I would be sharing the link to the form soon. So the form is live. Please fill it up. And that's all for the day. Thank you so much, sir. If you have any further information, do let us know.
No, nothing from my side. Maybe like if anyone is having any problems downloading, installing Unity, you can reach out to me through Akshat. I guess I'll connect with Akshat, and if required, we can create a WhatsApp or a Telegram channel, something like that, and depending upon what issues you have. One thing that we would like to discuss was basically I have been notified that your exams are coming up from 10th of June. So it depends on you if you want to continue the sessions. I've been told that the exams are online, so you don't have much problem. But if it depends on you whether you want to continue the sessions or do you want to stop and continue after the exams. So however you want to communicate over this, discuss amongst yourself and like let us know.
So just as a deterrence, we have put that in the form as well, sir. So we
Okay,
would
okay,
inform you about the results once we get there.
okay,
And
okay.
we have a question from Pranav. He is
Yeah.
asking, can we download Unity without logging in through GitHub?
Yeah. You can. It's not required. So GitHub student, I just told that because to get the pro version of the Unity, but you don't generally need to do that. You can download without going through that as well. You don't have to go through that process of connecting your GitHub and Unity accounts. You can download Unity as is. So yeah.
So I think that's all for today, sir.
Okay.
Thank you so much, sir. And we'll see you soon.
Yeah. Okay.
Thank you,
Bye.
sir.
Thank you everyone for joining.
Good afternoon, sir. Okay, as a reminder, everyone is requested to fill up the form as soon as possible.